Good morning, guys of grade 11. Welcome back. Today, inshallah, we're going to start the first session in quarter 4. So, we're going to pass to chapter 18, section 1, the nature of chemical equilibrium. So, first of all, we need to remember what the word equilibrium means or what this word means. So, equilibrium just give you a sense that there's two sides which are equal. So, what are the two sides which are equal and what meant by chemical equilibrium? Let's start here. First of all, we need to remember, okay, what we stopped at last quarter. Last quarter, we stopped at the types of solutions, and we said that solid could dissolve in solvent and so on. We passed to the part which we talked about the concentration of the solution and the solubility, and we said that the solution could be saturated or unsaturated or supersaturated, if you remember. So let's recall something here, okay, or let's remember something. So imagine that we have a cup of water, okay, and this cup of water contains a saturated solution of sugar. That means the water is already completely containing the large amount of sugar, and there is no more spaces between water particles to dissolve extra sugar. And in that case, we said if we are gonna add some sugar, okay, or extra amount of sugar, so what would happen in that case? Actually, we said we're gonna observe that the extra sugar just will settle down, or it will be at the bottom of the cup, but actually doesn't dissolve at all or actually dissolves a lot. To remember this, we said actually in the microscopic level, or we just keep focusing on the particles here, we're gonna find that some particles of sugar actually dissolve. And in the same time, okay, there is some particles of the sugar which is already dissolved in water will crystallize and settle down again. So here for the naked eye or on the eye level, we cannot observe this dynamic movement. Okay, we just observe there is some sugar settle down and they still the same amount. They never decrease or increase. But actually, some of these particles are dissolving in the same time, equal amount is crystallizing. So here we have two opposite processes happen in two opposite directions in the same rate. So we call this an equilibrium state. Okay. So here, like this equilibrium, we could imagine when we say that equilibrium, it means we have two processes that they work in two opposite directions in the same rate. So we call this an equilibrium. So like this here, that is a dynamic equilibrium. To get another example, okay, if we have this container, okay, and this container, for example, the cooking pan, which keep the pressure, okay, this which is completely closed, okay, so they are completely closed and there is no space, okay, to escape any gas or to enter anything. So, and we start to heat it up. So once we heat it up, what would happen? This water, after it heat, is going to change into vapor, okay? So this water vapor, so the vapor once it come up, okay, actually it will touch the surface and it will condense, okay. So in that case, we're gonna find that the amount of evaporation is gonna equal the amount of the condensation, okay, because this beaker or this container actually is completely closed, okay, and there is no way for some vapor to escape. Actually, if the vapor escaped, this equilibrium will be damaged, but actually because it's or there is no chance for vapor to escape, and the container is completely closed, so we find that the rate of evaporation will equal the rate of condensation. In that case, also we call this is a dynamic equilibrium. So both of these examples, they are physical equilibrium. That means there are physical changes that happen in two opposite directions in the same rate. We call this a physical equilibrium. Today, or in that section, actually, we are gonna pause, or we are just to keep talking about the equilibrium more and more. We will include talking about the chemical equilibrium. That means the chemical changes. How are two different chemical changes could happen in the same time in two opposite directions. Okay, so let's back here to our book. So like this, we get the idea or what the meaning of the word equilibrium in general. So we pass now to the reversible reaction. So reversible reaction that which represent the idea of equilibrium in a chemical exchange. So what is a reversible reaction? If you remember, we studied before in quarter 2 the signs or the symbols which we could find in a chemical equation. And one of these symbols that if we saw a double arrow like this, we call this it's a reversible reaction. So what meaning by reversible reaction? So simply by you looking at this symbol, we could remember that a reversible reaction, that the reaction which could happen in two opposite direction, in which the reactant simply they are going to react to produce the products, and then the products will recombine to reform the reactants again. So we call this, it's a reversible reaction that could work in a forward direction from reactant to the product, and the reverse direction or backward from the products to the reactant. So simply here we said that a chemical reaction in which, or it is the reaction in which the product could react to reform the reactants one more time, we call this a reversible reaction. Let's get an example to clarify the idea. So here, for example, we find that the mercury oxide, okay, so the mercury oxide, once it heated, okay, at good temperature or the direct heat, okay, as you could see here in this picture, we find that the mercury oxide actually will break down into mercury and oxygen gas. So in normal conditions or in normal situation, actually oxygen gas will escape out of the tube, okay, and in that case, okay, we get the result is mercury that will make this kind of precipitation at the bottom of the tube. But let's imagine if we just keep this tube is completely closed and we don't allow oxygen to escape from the container and it's keep trapped with the mercury. Actually, in the other hand, we could observe that mercury could react with oxygen once it heated gently and producing mercury oxide one more time. Actually, if you look, this equation is completely the opposite of this one, which means the R2 reactions happen in two opposite directions. We find the mercury oxide could break down, it's a decomposition reaction, producing mercury and oxygen, while in the other hand, we find that mercury could react with oxygen, that is a synthesis reaction, which is going to create the mercury oxide one more time. So if we keep a conditions that both are trapped inside the tube, we don't allow oxygen to escape, and we keep the heating, okay, or they keep heated and as a continuous process. So in that case, we're gonna find in the beginning of the reaction, some of the mercury oxide will break down to form mercury and oxygen. Once mercury and oxygen are free and found together in the tube, okay, under the heating process or conditions, they are gonna recombine to form mercury oxide one more time. And later we're gonna find we are gonna reach a case of equilibrium in which the rate, the breaking down of mercury oxide equal the rate of creating mercury oxide. So that means after time, we are gonna that two reactions will work together in the same rate, okay? And we are certain point we're gonna find the concentration of mercury oxide and the concentration of hydrogen and oxygen are equal. That means after certain time, once we reach the equilibrium, we're gonna find always for each 2 moles of mercury oxide, we have 2 moles of mercury and 1 mole of oxygen gas, and this ratio will be constant. So we call this, we are in chemical equilibrium. So here, like I said, this we said that chemical equilibrium, or we said a reversible chemical reaction, or in the chemical equilibrium, when the rate of its forward reaction equal the rate of the reverse reaction, and the concentration of its product and reactants remain unchanged. And that actually requires certain conditions, in the conditions which allow the two processes to work or the two reactions to work in opposite directions. So for example, here we need to trap the oxygen, doesn't allow it to escape, and also we need to keep heating, okay? So any one of these conditions, actually, if it changes, so the equilibrium will be missed, and actually these two reactions will not work in the two directions in equal rate, and we're gonna find that one reaction will work. So here, like this, as we can see for this equation, we just could combine the two equations in the same, in just one, and adding the two error into opposite directions, which means the reaction is already working in the two directions with the same rate. So here, like this, that represent the idea of chemical equilibrium. So let's see something here. So that means always in in equilibrium, the two sides or the two reactions, the forward reaction and the reverse reaction, they are working in the same rate or they are acting in the same rate. Actually, it's not like that. Sometimes we could find that one of the rate or one reaction's rate is somehow faster than the rate of the other one. So for example, in this one here, you could find that when sulfur dioxide is going to react with oxygen, it will produce sulfur trioxide. In same way, time, sulfur trioxide could break down into sulfur dioxide and oxygen. So here is the forward reaction, and that is the reverse reaction or the backward reaction. If we could look here, there is a kind of equilibrium, which means we have two reactions already working in opposite direction. We call this the reverse reaction. But as we could observe, if you look to the arrow or two arrows in that equation, you're gonna find that arrow somehow is longer than the other arrow, which means, okay, the rate of the reaction or the forward reaction in which the sulfur dioxide is gonna react with oxygen to produce sulfur trioxide, somehow this rate is faster, it's more favored, okay, it happens better, okay, than the other reaction. That means the rate of breaking down sulfur trioxide into sulfur dioxide and oxygen is less. So here we could say that as you can notice, the equation is written showing an equality of the two arrow lengths. So the forward reaction is represented by longer arrow, which means here its spirit or this reaction happened better than the other one, or it's favored. That means it's higher rate than the other one. Okay, so which means here, okay, that reaction, or in this situation, we're gonna find the concentration of this substance is not that equal all the time, because we got here and this equilibrium lies to the right, like to the right. That means this equilibrium just go to this direction more than the other one. Okay, so here like this, we could say the reaction is already working in that direction there. So we could have the opposite, as we can see here. Okay, here once we find that the carbonic acid H2CO3 is gonna react or dissociate in water, it's gonna break down into hydronium ion and bicarbonate polyatomic ion is free. So actually, once the bicarbonate ion and the hydronium ion are found, they easily react together and they produce carbonic acid and the water will multiply. So in that reaction, also once you look to these two errors, okay, you're gonna find the are not equal, which means this equilibrium, okay, they somehow lies to the left, right, in which that the rate of the reaction of the product is more to produce the reactants is more, which means actually in that case or in this way, it means already the dissociation or the breaking down of carbonic acid in water is weak, is not good, because already that is going to be reduced in rate less or lower than that rate. So that means in lab, practically, when you dissolve carbonic acid in water, it will break down into water and carbonic, but in that slow rate. That means the majority of H2CO3 will not break down, because at the moment they are break, okay, down like this, well, they recombine quickly to back again to the carbonic acid and the water. So here like this, we find that also there is another type. While here, once you look at this kind of part, guys, you could find that once sulfuric acid decomposes in water or that dissociate in water, it will produce hydronium ion and sulfuric acid, and they are in equal rate. That means the two sides are equally work at the same time. Okay, so like this here, you could find the amount of the sulfuric acid which will break down into hydronium and the hydrosulfate group. Okay, so these still the same, there is no difference. So like this here, we give an idea about the equilibrium, or today we just know what we mean by equilibrium, reverse reaction, and how we could, okay, represent that by the chemical equation. Next time, guys, we're going to talk about the equilibrium expression, and then we start to know how to calculate equilibrium and so on. Please study this part very well from your textbook, okay? And if you have any question or something not clear, I'm waiting for your answers. Thank you, guys, and goodbye.